Okay guys, and welcome to the video on intermolecular bonding. So first of all, I want to turn your attention to the periodic table. The aim of today's lesson is to go through bonding, not only intermolecular bonding, but all types of bonding in chemistry. So here we have the periodic table. Now on the left-hand side we have metals, and on the right-hand side we have non-metals. Okay, so basically in terms of bonding, if you're in groups 1, 2, or 3, new 13, you will react by losing electrons because you have 1, 2, or 3 electrons in your outer shell. If you're in group 4, you can go either way. And if you're in group 5, 6, and 7, you have 3 electrons in your outer shell, 2 electrons, and 1 electron. Sorry, you need 3 electrons to fill out your outer shell, 2 electrons, and 1 electron. So you will gain electrons. Okay, so we have 3 types of bonding. First type of bonding is between non-metals. Second type of bonding is between metals. And third type of bonding is between a metal and a non-metal. So the type of bonding between non-metals. Non-metals want to gain electrons. But if you have 2 things that both want to gain something, it's not like one of the things can give it to the other thing. It's that they'll end up sharing. So in non-metals, they are sharing electrons, and they're called covalent bonds. In metals, they both want to lose. They both want to lose electrons. So if you have something that wants to lose an electron, but the other thing wants to also lose, you end up with these unwanted electrons, and that's exactly what we see in the metallic bonding model. Sodium has 1 electron in its outer shell. It wants to remove that electron, but this sodium doesn't want it, so it releases it, and they end up playing ping pong with the electrons. Now a metal and a non-metal. Very interesting, because you've got a metal that wants to lose and you've got a non-metal that wants to gain. So let's have a look at sodium, for example, and chlorine. Sodium will donate its electron to chlorine. Sodium will become positive and chlorine will become chloride, which is -1. Together forming sodium chloride, which is an ionic compound. So ionic compounds only have a cation and anion. Okay, now within non-metals, we also have intermolecular bonding between molecules. So if we take ammonia, for example, N has 5 electrons in its outer shell, so it needs 3 bonds, and H has 1 electron in its outer shell. It needs 1 bond. Nitrogen will bond to 3 hydrogens to fulfill its outer shell, and it will have 1 lone pair. This is a molecule. A molecule is a small molecule. A molecule is a small, covalently bonded species. Okay? Now, within the molecule, you have what's known as intramolecular bonds, which are covalent in nature. But we know that these molecules are attracted to each other. Now, there are three main types of intermolecular bonds that can occur. So intermolecular bonds are bonds between molecules. Bonds or forces. Sometimes they're very, very weak. So you've got to ask yourself, when determining what type of bond it'll be, you have to ask yourself, is it polar or non-polar? Now, if it's a polar bond, it can be one of two things. If it has the definition of NO/F bonded to a H, it undergoes intermolecular hydrogen bonds. If it has, if it is not NO/F bonded to a H but it's polar, it's dipole bonding. If it is non-polar, it must be held together by dispersion forces. I guess, how do we determine if something's polar or non-polar would be a way to go. So, when determining whether or not something's polar, so how to determine if something is polar. Okay, so when determining whether or not something is polar, you need to look at, so one, you'll need to draw the molecule. I use the valence structure with the lines. You then need to look at, take each covalent bond as a tug of war of electrons. If we take this covalent bond, for example, so a covalent bond are the lines between the atoms. If we take this covalent bond, for example, just because they're sharing electrons doesn't mean they're sharing electrons equally. The electrons could either be closer to the H or closer to the Cl, and this all depends on their relative electronegativity. So if you have a look, I'm sure you guys remember this, but if you have a look at your periodic table, the most electronegative elements are closer to fluorine. So electronegativity increases this way as you get an increase in core charge and as you get a decrease in distance from the nucleus. So if you compare hydrogen to chlorine, hydrogen is a lot closer to fluorine. Chlorine is a lot closer to fluorine than hydrogen is. So it wins the battle and the electrons are closer to it. Therefore, instead of showing it with the electrons physically closer, we do delta negative and delta positive. It's not a full negative because the electrons are just closer to it. It hasn't gained electrons or an electron. Okay. So, you take each covalent bond as a tug of war of electrons and you basically designate delta positive to the less electronegative element and delta negative to the more electronegative element. Okay, 3. Then what you do is you find out if the bonds are polar, so that's first, and then you look at the molecule as a whole. You look at the molecule as a whole. You need to see if the molecule can be cut so that it has asymmetry in charge. So here we've got negative on this side, positive on this side. If it does, it's if yes, it is polar. Then it's easy after that. If it's polar, you just look NORF bonded to a H or dipole. So we may ask the following questions. What type of intermolecular bonding? And which one will have a higher boiling point? So we've got to look at the strengths as well. Now, hydrogen bonding is the strongest. Then dipole, then dispersion. Okay, let's explain a little bit about what these are. So dipole, as we saw before, note that the dipole bonding is intermolecular. So this is one molecule, this is another. This molecule is called polar. Well, this molecule is called a dipole, same thing. Dipole means that it has two poles. And this molecule is called a dipole, hence the bonding is called dipole. So this is an electrostatic attraction, and this is an attraction between positive and negative. Okay, and it is between the delta negative chlorine and the delta positive hydrogen. So it's a bond. But if we want to compare it, let's compare it to ammonia. Now, between the N and the H, the N is more electronegative than the chlorine. Well, it's NORF are technically the most electronegative elements on the periodic table. So when N is sharing with H, it gains a larger delta negative than the chlorine would be, because there's a greater difference. It's like if you've got a small person in a tug of war with a larger person, it'll be much closer to the larger person, but in H and Cl, you still got the H, which is a small person, but now you've got a Cl, which is just a medium-sized person, so it won't be as close to the Cl, giving it delta negative, but this one, it'll be a large delta negative, okay, and giving this one a large delta positive. Now, when ammonia is bonding with itself, so one ammonia molecule bonds to another ammonia molecule, this intermolecular bond, by definition, is called hydrogen bonding. Okay, let's have a look at dispersion forces. Now, if you look at something like iodine, because iodine has 2 atoms of the same element, they can't differ in electronegativity. It's like if you had a tug of war with people that are exactly the same strength. You'd get, it would go on forever. It would be right smack dab in the middle of them. So that's something to keep in mind. But we know that as you go down the periodic table, down group 7, all held together by, we don't know yet, but let's get there. Iodine is a solid at room temperature. Iodine's the heaviest. Bromine is a liquid. And chlorine is a gas. So you kind of think, because iodine is a solid at room temperature, it must have stronger intermolecular bonds. And they've found out that dispersion forces, this is what they have, nonpolar substances, are basically when, if all the electrons, or if you get an uneven distribution of electrons move to one side of a molecule just by chance, it'll actually have a delta negative side. If it's near another molecule, it'll push the electrons from this side of the molecule to that side. Delta positive, delta negative, and this is what you call a dispersion force. They are called temporary dipoles, and they constantly break and reform. But the way you increase the strength of a dispersion force is by 1, if the molecules, so stronger dispersion forces occur when molecules are closer together, or molecules have more electrons. More electrons, greater negative charge, greater influence on the other one. Closer, because if this was far away from that, it wouldn't be able to influence its electrons and they wouldn't bond together. So, we've got to talk about melting and boiling. Okay, so when you melt, like you melt water at 0 degrees Celsius, turns into a liquid. And when you boil water at 100 degrees Celsius, you don't break covalent bonds. Okay? You actually break the intermolecular bonds. So when deciding which one will have the highest boiling point, you have to look at which one has the strongest intermolecular bonds. Highest boiling point equals strongest intermolecular bonds. Okay, so let's have a look here. Okay, I want to do a couple of examples. I want you to consider the following substances And I want you to pause the video, and I want you to determine the type of intermolecular bonding Okay, so I'd suggest now to pause the video and try and answer the following questions. Rickman! Rickman! Shush! Okay. So Okay, so it's really important in this stage that we understand that the weakest form of bonding is dispersion forces. So all molecules, because it's just random the way the electrons are arranged, all molecules have dispersion forces. Now, if you've got dipole-dipole bonding, it means that you have dispersion forces and dipole-dipole bonding. But when you're picking what type of bonding a particular molecule has, you'd pick the strongest type of bonding because that would have the most significant effect on the intermolecular bonding. When you have hydrogen bonding, it's a special form of dipole-dipole bonding. So you have dipole-dipole and dispersion forces and hydrogen bonding, but you'd pick H bonding because it is the strongest. So let's have a look at these. So if we have a look at ammonia, we spoke about this before. This would be NO or F bonded to a H, therefore it has to be hydrogen bonding. F2O, oxygen has 6 electrons, F has 7, oxygen needs 2, F needs 1, so therefore you need 2 Fs. But you've still got 2 lone pairs, it's just like H2O, bent. Anyway, delta negative, delta positive, delta positive. So therefore it is polar, but it is not NO or F bonded to a H, it's an O bonded to an F, so it's just dipole-dipole. Okay, C. So CH3Cl, delta neg, delta pos, delta pos, delta pos, delta pos, delta neg compared to that, but regardless, still negative and positive, polar. There is no N or OF bonded to a H, so it's just dipole, dipole. Okay, now let's look at the next one. CH, Cl, Cl, Cl will be bonded to Cl, 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 delta positive, delta negative. They'll be attracted to each other by dipole, dipole bonding. Okay. Anyway, I'm going to go through them quite quickly. HBr is dipole-dipole. That's quite an easy one. H2S is dipole-dipole. G, HF. We have H, which is delta positive, and we have F, which is delta negative, and we have another H. Remember, it's intermolecular, not within the molecule, but between molecules. And this is NO or F bonded to a H, so it follows that definition of hydrogen bonding. H2O, we know, is hydrogen bonding. One water molecule can actually make 4 hydrogen bonds with 4 other water molecules. It's perfect. It's got 2 lone pairs and 2 hydrogens, which are positive, so 2 positives, 2 negatives. meaning that it's got a perfect number of positives for negatives, so forms 4 hydrogen bonds. Okay, and then we've got H2. Well, H2, because you've got two atoms of the same element, there's no difference in electronegativity. There's no delta positive, no delta negative, meaning it's just held together by dispersion forces. Then you've got methanol. Now, methanol, it's getting interesting now because you've got this OH which has delta negative and delta positive, but then you have these positives here. Now you look at, can I cut this in a way so that it's asymmetric? And the answer is yes. I'll draw that out a little neater. Because of these lone pairs, it has asymmetry just here with a delta negative here and a delta positive here, meaning that it can actually undergo hydrogen bonding. But this part is not the polar part, it's the OH that's polar. Similarly, if we look at ethanol, in much the same way, delta neg, delta positive, this part is polar, but this part is non-polar. This is why when you have a fatty acid, you've got such a long tail. Now eventually the polar part starts competing with the non-polar part, and there comes a time where it has a polar part, a definite polar part, and a non-polar part. So it's kind of both polar and non-polar, but that's fine. You just have to make sure you state which part's polar and why, and this part can undergo hydrogen bonding with itself. This part could undergo dipole-dipole bonding with itself, or it could undergo hydrogen bonding because it's got an oxygen if it's bonded to an OH, which is on another molecule. But this is the non-polar part, this is the polar part. This one got a lot of you guys. And this is L, okay? Now, if you look at this, yep, delta negative, delta pos, delta pos, delta pos, a definite polar molecule. But if you look at the strictly speaking definition, it's a carbon bonded to a fluorine. It's not an NO or F bonded directly to a H, so it's actually just dipole-dipole bonding. Okay, now I want to go through some sort of VCAR level questions that they may ask you. I'm just going to write down a number of questions that VCAR has asked, and I want us to answer it. So which molecule, heptane or octane, will have a higher boiling point? Explain. Well, if you have a look at hydrocarbons, because they're just made of C and H, they're all non-polar. So they undergo dispersion force attractions. I'm just planning out our answer. Because octane has more electrons, it has a higher molar mass, it has stronger dispersion forces and a higher boiling point. So the way we should answer this question to gain our, let's say that this is 2 marks, we'd need to say that both heptane and octane are non-polar molecules. Hence, the type of intermolecular bonding they experience is dispersion force attraction. The strength of dispersion force attraction depends on molecular size / number of electrons. Therefore, octane has stronger dispersion forces, meaning its boiling point is higher. Okay, the next thing we may get asked, would 1-methyl butane have a higher, shouldn't be a space there, or lower boiling point than pentane? You have a look at the formula of these two. Pentane is C5H12. 1-methyl butane is also C5H12, so you can't explain it in terms of electrons. But you can explain, because 1-methyl butane has a branch and pentane is just a chain, chains will pack together closer than a branch. They can't physically pack as close. So if you look at the attraction between these two compared to these two, this one is stronger as they are closer together. If I repeat that from the notes before, where I have notes. Here. Here we go. Stronger dispersion forces occur when molecules are closer together. So when you get branching, you weaken the dispersion forces, or molecules have more electrons. Because these have the same electrons, you can't explain it in terms of that. So you should say a lower boiling point, because 1-methyl butane has a branch, the molecules cannot pack as close together, lowering the dispersion force attraction between them and lowering the boiling point. Okay? Another thing that they may ask is but-1-ene versus butane. Now I know they have a slightly different formula, so butane would be C4H10, but-1-ene is C4H8. So slightly different number of electrons, but their boiling point is different. But-1-ene has a double bond, butane has a single bond. So when you get a double bond, what you do is you create a kink in the chain. When it's all single bonds, everything has a tetrahedral arrangement. But when you get a double bond, you create a kink which is triangular planar. So you create a kink, so you can imagine if I drew this out with the skeletal formula, tetrahedral would be like so, and if you've got something with a kink, it would actually go like this, meaning that they can't pack as close. So we also said that there, we said dispersion forces are higher when molecules are closer together. So the way you'd explain this is butane has a higher boiling point because it is saturated. Molecules can pack closer together, whereas but-1-ene has a double bond, creating a kink in the chain, meaning that molecules cannot pack as closely together, lowering the dispersion force, attraction, and boiling point. Which would have another thing they might ask is rank the following in terms of boiling point. And they may have chloromethane, regular methane, and methanol. Well, let's draw them out. Chloromethane, methane, and methanol. Remember, it's intermolecularly, so how they're going to be attracted to each other. Let's have a look. So, you've got chloromethane. Now with chloromethane, you've got a delta neg here, and you've got definite delta positives here. It's not an NRF bonded to a H, so it just has to be dipole-dipole as the strongest form of bonding. And then here we've got delta pos, delta pos, delta pos, delta pos, all the same distance apart. Therefore, it's non-polar and dispersion forces. Then we have delta neg, delta pos, delta neg, delta pos, these will be attracted to each other. We have an NO/F bonded to a H, so we have the strongest form of bonding as hydrogen bonding. You'd expect the highest boiling point here, second here, and third here. And you would simply say methanol highest as hydrogen intermolecular bonds are stronger than chloromethanes dipole-dipole bonding and methanes dispersion force attraction. Okay, so you have to always say, when answering these questions, you have to say the type of bonding, relative strength, and so you have to say the type of bonding, then you have to say the relative strength of it, and then you have to relate to boiling point. Stronger bonding, higher boiling point. Put this under here. You guys can pause the video and have a go at answering it if you want. So it says that, just try and focus. It says that the compounds in the table below have the same relative molecular mass of 74, but have different boiling points. In terms of structure and bonding, explain why diethyl ether has such a low boiling point compared to the other two compounds. So we have something with the highest boiling point, which is propanoic acid. So we know that propanoic acid has the highest boiling point, and it is like so. And then we have 1-butanol, which is like so. And then we have diethyl ether, which is like so. Okay, so let's have a look in terms of intermolecular bonding. Okay, so with diethyl ether, we have to have a look. Now, oxygen shows a little bit of polarity here, but it's a very small amount of polarity. It would actually undergo mostly dispersion forces. So you'd have to say diethyl ether molecules show little polarity, and are thus held to each other and are held together by weak dispersion forces, mainly. With the other two, propanoic acid and butanol, they can undergo hydrogen bonding. Butanol, well, 1-butanol and propanoic acid. Hydrogen bonding is stronger than dispersion forces, meaning that they will have a higher boiling point. I said the type of bonding, yep. I said the relative strength, yep, and I related it to boiling point. That's what you've got to do. That's the method to success. Well, I hope that helped.